So for our first example, we're going to compute the singular value decomposition of this matrix here. So the first step in doing so is, let's use blue, is we're going to find the eigenvalues of A transpose A. Okay, now A is not a square matrix, so of course it doesn't have eigenvalues, but A transpose A is square, and so we can compute its eigenvalues. So first of all, we're going to take A transpose A, figure out what that is. When we compute that matrix product, we get 2, 1, 1, 1, 1, 0, 1, 0, 1. And you'll notice this matrix is symmetric, as it should be. It should always be symmetric when you're doing this. Now this is actually a matrix we looked at earlier, or we saw last class. And we computed the eigenvalues, so we computed the characteristic polynomial. We found the roots of the characteristic polynomial, and those roots were the eigenvalues, which are lambda 1, the biggest one was 3, the next biggest was 1, and the next biggest was 0. Okay? So that tells us then that our singular values of A are sigma 1 equals square root of 3, sigma 2 is the square root of 1, which is 1, and sigma 3 is the square root of 0, which is 0. So this gives us enough information now to build our sigma matrix. So remember, sigma is just going to be a matrix that's the same shape as A, so it's going to be a 2 by 3 matrix. And the way we build it is we plug in the singular values on the diagonal and then fill in everything else. Okay? Now notice we didn't actually, if we wanted to sort of plug in each of these singular values, we actually didn't have enough space to plug them all in. However, the last one was 0, and that's not a problem if we don't have enough room for the 0 singular values. You'll always have enough room for the non-zero singular values because remember, the number of non-zero singular values is the rank of the matrix, and there's always, if your rank is 5, then you will always have at least 5 columns and at least 5 rows. Okay? So you'll always have enough room for the non-zero singular values, but you might not have enough room to sort of plug in those 0 singular values, and that's okay. So that's sigma. The next step is we want to find the columns of V, meaning we want to find the orthonormal eigenvectors of A transpose A. So let's find orthonormal eigenvectors of A transpose A. Okay. So we're going to do this once for each of the eigenvalues we found for A transpose A. So for lambda 1 is equal to 3, we're going to compute A transpose A minus 3 times the identity. So we're going to subtract 3 off the diagonal of A transpose A. So it's going to give us negative 1, 1, 1, 1, negative 2, 0, and 1, 0, negative 2. Okay. Now if we row reduce this, just eyeballing this, I think it's going to be 1, 0, negative 2, 0, 1, negative 1, and 0, 0, 0. So just to make it clear, I didn't eyeball that. I mean, maybe you could, but I had the answer written down. But all I did was row reduce this. And so if you can't just eyeball it, don't feel bad. I don't think I could eyeball it either. So the top row is going to give us the equation x minus 2z equals 0. Second one is going to give us y minus z equals 0. So that tells me then that x, and the variable z is free. So therefore x is equal to 2z, y is equal to z, and therefore my vector x, y, z, I'm running out of room here. Maybe I should just go to the next page here. I don't want to make it too cramped. So that tells me then that my vector x, y, z, and sorry for the changed pen thickness, the template changed here, but so x, y, z, x is equal to 2z, y is equal to z, and of course z is equal to z. So I can pull a z out, and that gives me z, which is my free variable, times 2, 1, 1. Now, ultimately, I'm going to want this to be a unit vector because we want to make an orthonormal basis. So I'm going to normalize, and when I normalize, I'm going to call the resulting vector v1. So I'm going to divide by the norm of that vector. The norm of that vector is 4 plus 1 plus 1. That's 6. So that's the norm is rad 6. So I'm going to divide everything by square root of 6. So I get 2 rad 6, 1 rad 6, 1 rad 6, and that's my v1 vector. I'm going to do the same thing for the other eigenvalues. So lambda 2 was 1, and for this eigenvalue, when I'm going to subtract 1 off the diagonal here. So this is going to give me the matrix 1, 1, 1, 1, 0, 0, 1, 0, 0. When I row reduce this one might be easy enough to row reduce by just looking at it, but you get 1, 0, 0, 0, 1, 1, 0, 0, 0. And so this tells me then that x is equal to 0, y plus z is equal to 0, and z is free. And so that tells me x is 0, y is negative z, and z is free. So my vector x, y, z becomes 0 minus z, z. And if I pull out my free variable, okay. Now, of course, I want to normalize again. So when I do, I'm going to divide by the length of that vector. And the length of that vector is square root of 2. So I get 0, negative 1 over square root 2, and 1 over square root 2. And so that's my second vector. Sorry, my son just came in. I'm not sure if he's going to ask me a question. He's just kind of watching, I think. So, lambda 3 is equal to 0 is our last eigenvalue. And so we take A transpose A, and we subtract 0 times I off the diagonal. That just gives us 2, 1, 1, 1, 1, 0, 1, 0, 1. And when we row reduce this, we get the matrix 1, 0, 1, 0, 1, negative 1, 0, 0, 0. And that tells me that x plus z is 0, y minus z is 0, and z is free. So x is equal to minus z, and y is equal to z. So my vector x, y, z just becomes minus z, z, and z. After pulling the z out, I get that. And if I normalize like I did before, I get my v3 is equal to, so the norm of this is rad 3, so this will be negative 1 over rad 3, 1 over rad 3, and 1 over rad 3. Okay, so those are my 3 v vectors. And with this information, I can now build my v matrix. So my v matrix now is just 2 over rad 6, 1 over rad 6, 1 over rad 6, 0, negative 1 over rad 2, 1 over rad 2, and then negative 1 over rad 3, 1 over rad 3, 1 over rad 3. Okay, and so you should notice that this matrix has orthonormal columns, so it should be an orthogonal matrix, which again means it's a square matrix with orthonormal columns. You can check that quite easily. If it is, then that's a good indication you're doing things correctly. If it's not, then you may have made a mistake somewhere. But that's at least sort of a partial check you can do along the way. Now that we have our sigma matrix and our V matrix, the last step will be to find the U matrix. So we're going to find the columns of the U matrix, okay? And so to do this, remember we have this formula that U1 is equal to sigma 1, or sorry, 1 over sigma 1 times A V1. So over here, for sigma 1, that's rad 3, if you'll remember. Our matrix A is 1, 1, 0, 1, 0, 1. And then we times this by our V1 vector. So when we multiply by A, we're going to get 3 over rad 6 for our first entry. And our second entry will also be 3 over rad 6, but that actually reduces down to, well, rather, if we divide through by rad 3, that's going to give us rad 3 over rad 6, rad 3 over rad 6, which is also sometimes called 1 over rad 2. 1 over rad 2. So that's our first U vector. Our second U vector is determined similarly. So this gives us negative 1 over rad 2 and 1 over rad 2. And so with those two vectors, we, again, remember the shape of, if A is an m by n matrix, so if A is m by n, then U should be m by m. In this case, A was 2 by 3, so U is going to be a 2 by 2 matrix. Okay? And since we have enough columns to build the matrix U, we just have to plug those in. So we're sort of doing the same order with everything. All the vectors go in the same order, corresponding to sort of the order of the singular values in decreasing order. So we just sort of preserve that same order everywhere. And this gives us the U matrix. Now, again, that third singular value was 0. Sigma 3 was 0. So we only did this procedure with the two singular values that were non-zero. And in this case, that gave us enough vectors to fill up the matrix U. Now, you should be able to check that U is an orthogonal matrix, meaning it's a square matrix with orthonormal columns. The reason those columns are orthonormal is, remember we had that proof on Friday that showed that the AV1 and AV2, well, essentially we had this proof that AV1 all the way up to AVR, where R is the number of non-zero singular values, this is an orthogonal basis for the column space. So in particular, these vectors should be orthogonal to each other. We also saw that the length of AVI is equal to the ith singular value. So the reason we're sort of dividing by these singular values here is to essentially normalize the vector. So the vectors you should end up with should be orthogonal, and they should be normal vectors. So they already should be an orthonormal basis for Rm. Okay? So you shouldn't have to normalize here. So now we have our U matrix, we have our V matrix, we have our sigma matrix. So the last step is just to plug them in. Okay? So this is what we've done. We sort of wrote these down here. And I guess I maybe wrote this a little bit differently. I simplified it a little bit differently, but plug them in, and you can always check your work here. Okay? So if you check your work and you find that this is an orthogonal matrix, this is an orthogonal matrix, and both of them have the right size, and this is one of these pseudo-diagonal matrices, and when you multiply them together, you get the original matrix, then you're almost 100% guaranteed to have done things correctly. So you can always check your work with these, which is pretty nice. So that does it for this example. We'll do another example in the next video.